Well, good morning. Today we are going to do the first half of Chapter 8. Before we get started, let me just say it's a very exciting day. Everyone finally gets to use the little log button on your calculator. So, make sure you dig out your calculator, look at it, and find the log button. And the 10 to the x button as well. Everybody's calculator is different. It's really important that you figure out how to do these operations on your calculator because we're going to do a lot of these logarithmic conversions. All right, Chapter 8 deals with acids and bases. Today we're going to go through just the background, and then we're going to move into the concept of pH. Now back in Chapter 7, long time ago, we did this problem in class where we have sulfuric acid reacting with sodium hydroxide. We made sodium sulfate and water. We were told we had 300 mils of 0.02 molar sodium hydroxide. We have a 100 mil sample of sulfuric acid. And what we did was to simply calculate the concentration, the unknown concentration of our sulfuric acid solution. Let's just go through this again. It basically is a simple problem based on Chapter 7. We know a concentration and a volume for our sodium hydroxide. Therefore, because concentration times volume is moles, we know how many moles of sodium hydroxide it took to react with the sulfuric acid that we had. Now you look at the stoichiometry here. It takes 2 sodium hydroxides for every sulfuric acid. So once we know the number of moles of sodium hydroxide, we're going to divide that by 2 to get moles of sulfuric acid. And finally, once we know moles of sulfuric acid and we know its volume, number of moles divided by volume in liters gives us molarity. So that's our logic and how we do this. Our moles of sodium hydroxide are simply concentration times volume. Remember to always convert things to liters. Do our calculation here. We have 6.45 times 10 to the minus 3 moles. Now our stoichiometry, 2 sodium hydroxides for every sulfuric acid. This is a model of sulfuric acid. You'll note we have a sulfur in the middle. We have 4 oxygens around, so it's a sulfate, isn't it? Except we have placed hydrogens on 2 of the oxygens with the sulfate. Every hydrogen brings in 1 positive charge. Sulfate would be -2, therefore this is neutral. And we're going to react this with sodium hydroxide. The hydroxide is going to pull off these 2 hydrogens, and we'll wind up with sulfate, sodium sulfate, and 2 moles of water. All right, well our stoichiometry is 2 to 1. Which means we're going to take the moles of sodium hydroxide. Every 1 mole of sulfuric acid takes 2 sodium hydroxides, so they cancel. And we get 3.23 times 10 to the minus 3 moles of sulfuric acid. And finally, to answer the entire problem here, what's our concentration? We know the number of moles. We know the number of liters. And our sulfuric acid at a concentration of 0.0323 moles per liter. So this is what we did in Chapter 7. Just kind of an intro to Chapter 8 here. Well, these types of reactions are neutralization reactions. Here we're taking an acid and a base and we're making water and a salt. The way these things work, sodium hydroxide and water, simple ionic compound, it ionizes to give sodium cation and hydroxide anion. Like I said, sulfuric acid, these two OHs here, ionize and they form hydronium. So hydrogen goes with water to form H3O+, and we're left with a sulfate. In our actual reaction, we're going to take a hydronium and a hydroxide, combine them to make water. So we start off with solutions that are strongly acidic, strongly basic, and we wind up with water. Any questions? Well, everything in chemistry comes back to water sooner or later. We've talked about water back in Chapter 7. We said that because the hydrogen and the oxygen differ in electronegativity, that the covalent bond between these two is polarized. We show that with little dipoles, and we remember that this means that this end of the molecule is going to be positive, and this end up here is going to be negative. That is, we have a molecular dipole that looks like this. In our molecule, we have a positive end down here and a negative end up by the oxygen. Now, we use this to rationalize how water can take a crystal apart and dissolve an ionic substance. We said that as the ions are removed from the crystal, that they are surrounded by waters, and in doing so, the water orients itself so that for the anion, the positive ends of the water dipole are all pointing towards the anion, and for the cation, the negative ends of the dipoles all point towards the cation. We saw some computer simulations that showed how this can stabilize the charge by dispersing both the negative and the positive charge over the adjacent water molecules. Any questions? All right, well, if water can interact with ions and do something as remarkable as take ions and put them in solution, it makes sense that water can interact with itself. Let's start off just with a molecule of water. We know that the OH bond is polar. We know that this end is positive, this end is negative. If I take another water molecule and bring it up next to this one, I can form a hydrogen bond. Hydrogen bond is going to be between the negative end of this dipole and the positive end of this oxygen-hydrogen bond. Hydrogen bonds. Hydrogen bonds are real. They're kind of like covalent bonds, except they're not very strong. in terms of kilocalories per mole, which nobody uses anymore, but I think that way. Kilocalories per mole. The bond for the OH is about 100 kilocalories worth of energy. That's how much energy it would take to break it. The bond that you get in a hydrogen bond is worth about 5 or 6 kilocalories. So it's a small amount. Let's go ahead and color this in. Bring in our full dipoles. And again, you see the hydrogen bond goes from the electron donor end here up to this OH bond, something like that. And again, that's worth about 5 kilocalories. Now, if you think about water, we have 2 OH bonds, don't we? So we could easily bring another one in. And if we do that, we can form hydrogen bonds here and here. So now we're talking 10 kilocalories or something. It's getting more interesting. And don't forget we've got a big red splotch up here. I could bring another one in, turn it like this, and I could form yet another hydrogen bond. This has 2 more hydrogens here. It can bond with 2 more oxygens. Same thing here. Find an oxygen here, another hydrogen out here, etc., etc. This process can go on indefinitely in water. That's why water is such a unique solvent, such a unique substance. It can form an indefinite array of these hydrogen bonded complexes. This just shows 1 water molecule with 4 waters around it. Again, we're coming in twice on our oxygen, coming in here with an OH, here another OH. These are the hydrogen bonds. Now, hydrogen bonds make and break very, very quickly. Every 1 microsecond, so 1,000,000 times a second, these bonds will make, rearrange, and then break, rearrange, whatever. But on average, these things are bonded to at least a cluster of 8 water molecules. That's kind of like the given size of the cluster. This here is a calculation of a fairly large cluster of water, and we have included hydrogen bonding in this calculation. And what I'd like to point out, what I'd like you to notice, is that you can see this hydrogen bonding here, can't you? Here's 1 OH, actually it's being swallowed by this guy. And this one's halfway into here. Down here, same thing. This is very, I mean, look at this guy. That's really swallowed it, hasn't it? This is really significant. Now, remember, it's transient. It rearranges constantly. But when you put all of these 5 kilocalories per moles together, you wind up with an incredible amount of energy. Water is the best substance we know for forming extended hydrogen bond networks. All right. Well, we've all heard of hydrogen bonding. Biology, we talk about hydrogen bonding between base pairs. Remember hydrogen bonding. You simply need something with electrons to serve as an electron donor, and you need a polar something hydrogen bond to serve as an acceptor. This is guanine, this is cytosine. If you look up here, we have an NH. Well, the electronegativities of nitrogen and hydrogen are different. So this is polarized. This is the positive end. Here's an oxygen. we can form one hydrogen bond there. In the middle, this nitrogen has a lone pair of electrons, doesn't it? This is another NH. We can form a second hydrogen bond right here. Down here, just like up top, have an NH and an oxygen. And we get a third hydrogen bond. The hydrogen bonding in the base pairs matches up very nicely like this. And that, again, they're not worth a whole lot of energy by themselves. But if you put three of them together, again, you're talking a lot of energy. In a DNA helix, this is a helix, and here is kind of being opened and unwound and stuff like that. These are examples. This is adenine, that's thymine, and here we have two hydrogen bonds we can make. Here we have a GC pair with three. Here's a two, here's a three, etc. Holding all this together, we have a phosphate deoxyribose backbone. Deoxyribose is just a sugar, except instead of an OH group here, we have a hydrogen. That's why it's called deoxy. And this is a phosphate backbone going up and down each chain. As these individual chains wind together, very important thing happens. As we wind them up, what we're doing is we're squeezing out water. That's very important. Here's a space filling model of this. Here you can see the phosphate backbone. That's this stuff. The gray is the ribose. But look down here. Here's the bases. And they're paired up. They're stacked, one on top of another. And they're hydrogen bonding across here. The way the geometry of this is, there is no room in between the bases for water. That's very, very important, actually, because water is so good at hydrogen bonding that out in this region where it's open, these bases would have virtually no affinity for each other. They would just hydrogen bond with water. Squeeze the water out, and you can get very, very efficient hydrogen bonding. So that's how hydrogen bonding works in biology. It allows bases to recognize each other, etc., etc. But hydrogen bonding in water does one other thing. Let's take a pair of water molecules and let's just let them sit next to each other and hydrogen bond. Now we've seen that calculation. We know that actually this oxygen has half swallowed this hydrogen, hasn't it? What if you came up and you just kind of gave it a little bump? Just a little nudge. What would happen? Well, by gosh, the hydrogen is transferred along the hydrogen bond. And when it does that, we form hydronium ion and a hydroxide. Now again, they're still sitting next to each other. This guy can hand it back. And we're back to two waters that are simply hydrogen bonded. I can sit here and push the button and do this all day. It's fun. This is what's known as the autoprotolysis of water. Sometimes called the autolysis, autoprotolysis. It's the spontaneous transfer of a hydrogen from one water molecule to the other. This process goes on constantly, very, very rapidly in water. In pure water, 100% pure water, the concentration of hydronium and hydroxide from this process, concentrations are both 10 to the minus 7 moles per liter. Spontaneous ionization. Any questions? Now we'll see that this autoprotolysis, is a very important thing. And this number, 10 to the minus 7 molar, is also going to be very important to us. But the point I want you to take away right now is that in pure water, at 25 degrees centigrade, concentration of hydronium and hydroxide are both 1 times 10 to the minus 7 moles per liter. This ionization goes back and forth very, very fast, like I said, a microsecond. Actually less than that for the ionization. But nonetheless, it goes on constantly, very, very rapid reaction. Now, just like we did when we were talking about ions, let's just address the question, how in the world is this possible? Remember I said that nature abhors a point charge. And here, just spontaneously, we took two neutral things and made a charged pair. Well, the reason this works, quite simply, is that the hydronium ion and the hydroxide ion, even though they're very highly charged species, are surrounded by this huge shell of water. And because they're surrounded by this huge shell of water, we're going to stabilize this charge. Let's just look at the hydronium, because it's easy. This is H3O+. If we do electrostatic potential map, there's our oxygen in the middle. We have a big blue belt around here. Tip it on its side a little bit. You can see the whole bottom half of this is just really rich blue. So very electron deficient. And even the oxygen end here barely comes up green. So a very electron deficient molecule. I'm going to take this just like we did with the sodium cation, and I'm going to place this in the middle of 3 water molecules. Now remember, this is hydronium, and it looks like that. When I take and do the calculation for all 4 of these molecules, hydronium and 3 waters, the electrostatic potential map looks something like this. Once again, we have taken and we have spread the charge away from our big blue, our big blue ball here. And we've spread it out over all of these molecules. Now, as I said, every water molecule is surrounded by, about 8. Here I've got 1, 2, 3, 4, 5, 6, 7, 8. Some above, some below. So this is kind of like a cluster with a hydronium here in the middle. So there it is, just sitting there, nice and cute. And I'm going to do the same thing. I'm going to calculate the surface for the entire cluster of 8. You'll notice how all the waters are arranged. Hydrogen bonding here, 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 everywhere. Plus hydrogen bonding in to the hydronium. When we do the calculation, it actually looks something like this. Now this guy in the middle, this is our hydronium. Remember? Green top, big blue bottom. That's all gone. In fact, the oxygen is now pretty much a bright red. This is just a phenomenal effect. This is the thing that makes water so incredibly special. All right, so let's say what we know here. We know that water is going to form extended hydrogen bond networks. That we can get transfer of a proton, we're going to call this proton transfer, along these hydrogen bonds. And when we do that, we make hydronium and hydroxide. In neutral water at 25 degrees, the concentration of hydronium, this guy, and hydroxide are both, they're equal, and they're both 10 to the minus 7 molar. Any questions? All right. Let's just sit back and appreciate what happened again a little bit more. When we transfer this proton, if you think about it, we broke a covalent bond, didn't we? So water is so good at stabilizing these ions that it's actually okay just to break a covalent bond. The thing is that water doesn't just do it to other waters. Let's look at our old friend, hydrogen fluoride. We remember that hydrogen fluoride, fluorine is the most electronegative element. And because of that, we have a very, very polarized covalent bond here. Well, if we take hydrogen fluoride and we put it into water, water's going to hydrogen bond here, and we're actually going to break the HF covalent bond. What happens is we take HF, put it in water, we're going to form hydronium and the fluoride anion. The process is very simple. Here we have water, hydrogen bonding to HF. Just like what happened in water itself. Just put a tiny touch of energy into this thing, and this transfers. Now it's going to go without electrons, isn't it? Leaves the electrons behind. If you have a hydrogen with no electrons, that's a proton, isn't it? Hydrogen atom has a proton and electron. So if we transfer it without the electron, this is a proton, it pops over, we get hydronium and fluoride anion. Now this is amazing, actually. Once again, we're breaking this polar covalent bond to form a pair of ions. Well, this process goes on in the forward direction. And just like we saw with water, it can also go on in the reverse direction. That is, hydronium can hydrogen bond to fluoride and basically hand the proton back. So we have a reaction here that spontaneously is going forward and back. This type of reaction is called an equilibrium. In an equilibrium, we have a reaction that goes this way and that way. The two reactions are distinct chemical reactions. This is ionization. This is going back to form our HF. And when we're going to show an equilibrium, we show it using a special arrow. This is a set of double arrows. Now remember when we did resonance, we had a double-headed arrow, didn't we? That's only used for resonance. When we have an equilibrium, we use two arrows, one this way and one that way. Any question? We would refer to this as the equilibrium ionization of HF. Now, here we have a reaction and we're generating hydronium ion. When we have hydronium ion being generated, that is referred to as an acid. HF is acting as an acid, donating a proton to water to make hydronium. When we say that HF is an acid, what we're saying is that it can donate this proton to give hydronium. Now there are two basic descriptions of acids and bases in chemistry. The one that we'll talk about mostly is going to be the Bronsted acid-base theory. You need to remember this is important. A Bronsted acid is simply a proton donor. A Bronsted base is a proton acceptor. So in this reaction, HF is a Bronsted acid donating a proton. The thing accepting the proton is water, and it's a Bronsted base. Now, among acids, we're going to have two groups. We're going to have strong acids and weak acids. The only real difference in the two is the position of this equilibrium. Now, let's talk about what we mean by that. Once we get this reaction going, once the ionization starts, if we had, or you could imagine a situation where we would have equal concentration of HF and F minus, and therefore hydronium. If the two concentrations were equal. So let's just start there. However, if this reaction going back was much, much faster than the one going forward, that is, if recombination was much, much faster than going this way, then instead of having equal quantities, we'd have much more of this than we would these guys. The less hydronium you have, the weaker the acid. So if we say this is a weak acid, what we're saying is this back reaction goes very, very fast, so as soon as you form it, boom, you're back here again. So almost everything here is going to be HF. If we had a strong acid, that simply means that going this way is really, really fast, and this way is slow. So we're going to take these, boop it all over here to hydronium. There's virtually no HF in solution. That would be a strong acid. Strong acid, lots and lots of hydronium. Weak acid, very, very little. Now in general chemistry, you're going to do this right. You're going to deal with not just strong acids, but with weak acids. Do lots of really neat calculations. We're not going to do that in 110, unfortunately. I'd love doing that, but we're not going to get to do that. Let's look at an example of a strong acid. This is HCl. HCl is an acid. It's a strong acid. When we take HCl and we put it into water, we ionize to form hydronium and chloride. The process of going forward is very, very, very fast. Process of going back is very, very slow. So that means that once you make these things, they stick around. Virtually all the HCl winds up as hydronium and chloride. Now, if you don't believe me, let's listen to the believable woman.
A strong electrolyte is a compound that ionizes completely in solution. Hydrogen chloride breaks into hydrogen and chlorine ions.
Now, first thing that I want you to note is she called this an electrolyte, didn't she? If you started HCl and water would have no ions in it, would it? Remember we said something was an electrolyte if it formed ions and therefore it conduct electricity. So here we're starting with HCl and water. Soon as they start to ionize, it goes essentially 100%, 99.9999% is present as hydronium and chloride, and maybe 1 part per billion of HCl. Any questions? All right, well, like I said, we're going to deal mostly with strong acids here. Common strong acids. We just saw HCl. HCl ionizes in water to give hydronium and chloride. We talked about nitric acid. Nitric acid would take nitrate, that's NO3, and we put a hydrogen on one of our oxygens. That's nitric acid. It ionizes to form nitrate and hydronium. Perchloric acid, chlorate, ClO4, perchlorate, ClO4 minus. We take, this is it, take one of the oxygens, put a hydrogen on, that's perchloric acid, reacts with water to give hydronium and perchlorate. Now, all of these acids, I put HCl here, HBr is a strong acid, HI is a strong acid. Actually, it turns out that HF is a weak acid, so we'll deal with that in 140. Nitric acid, perchloric acid, etc. All of these ionize to form 1 mole of hydronium, right? Because of that, these are called monoprotic acids. Monoprotic simply means 1 proton. Remember, this thing is transferred to water without electrons, so it's transferred as a simple proton. Monoprotic. An example of a diprotic acid is sulfuric acid. As we saw, we have 2 hydrogens attached to oxygens here. So we can rip the first one off and form hydrogen sulfate. Hydrogen sulfate, however, is still an acid. This can lose another one. We wind up with 2 moles of hydronium. Again, it's a diprotic acid. In your lab, you also did phosphoric acid, H3PO4. That's a triprotic acid. It's actually a weak acid, but triprotic acid. Any questions? Simple nomenclature. All right, well, there's one other concept that we want to grasp here. And this is, we know, we've talked about this being a Bronsted acid, and in this reaction, this is the Bronsted base, right? Proton donor, proton acceptor. Well, there's something also known as a conjugate acid-base pair. Now, in this reaction, nitric acid is reacting with water to give hydronium and nitrate. Okay, monoprotic. Isoprotic acid, we can do this. We know that nitric acid is our Bronsted acid because it donates a proton. Water is the Bronsted base because it accepts the proton. However, we can also describe this in terms of nitric acid being a Bronsted acid and having a conjugate base. If we describe nitric acid here as a conjugate acid, when we take its proton off, we generate nitrate, which is now referred to as its conjugate base. This is a conjugate acid-base pair. So when this thing acts like a Bronsted acid, it generates its conjugate base. When the base acts like a Bronsted base, that is, it accepts a proton, goes back to give its conjugate acid. The acid gives up a proton to form its conjugate base. Look at these and describe for each of these acids which is the conjugate acid and what its conjugate base is. The way you do this is to look at the reaction and say, what is the Bronsted acid? HCl. When HCl loses a proton, what does it form? Chloride. This is the acid form. This is its conjugate base. If the conjugate base accepted a proton, what would it form? Its conjugate acid. If this acted like a Bronsted base, it would form its conjugate acid. This is the first ionization of sulfuric acid. We'll describe this as first and second, okay? The first ionization, we're going to lose a proton to form hydrogen sulfate. The Bronsted acid here is sulfuric acid. When it loses its proton, it forms its conjugate base, which is hydrogen sulfate. Going backwards, if hydrogen sulfate acted as a Bronsted base, it would accept a proton and it would form its conjugate acid. The second ionization, we're starting now with hydrogen sulfate. It's going to lose a proton. This is the Bronsted acid, and this is its conjugate base. For our last reaction here, this is liquid ammonia. Turns out that liquid ammonia shares many of the properties of water. It's kind of a poor man's water, if you will, except it's very cold. It can support ionization, but not nearly as well as water can. If you had an ocean filled with liquid ammonia, you could imagine where it would be possible to have life in there. A different type of life than we have, but the same sort of chemistry might apply. Nitric acid, acting as a Bronsted acid, is going to lose a proton to form its conjugate base. Now in the back reaction here, here's my question to you. In the back reaction, So we're going this way. Identify the conjugate acid-base pair. In the back reaction, who's acting as a Bronsted acid? Who is the proton donor? Ammonium. Ammonium is going to donate a proton to nitrate. So this is, for the back reaction, this is the acid, and this is its conjugate base. Now everybody always has questions. Therefore, we have tutorials. In this, you actually get to type in a structure, but you obviously can't do charges or superscripts or subscripts. So you just put the numbers in, that'll work. And you do exactly the same thing on Blackboard. Here we have something and something giving rise to fluoride anion and hydronium. What you're supposed to do is simply fill them in the same order. So this block for here, this block for here. Now the logic. We're forming fluoride, aren't we? What gives up a proton so that fluoride is its conjugate base? What loses a proton to form fluoride? Obviously, that's HF. Here, we need a Bronsted base that's going to form hydronium. The Bronsted base here is simply water. Yeah.
I have like no idea how you got any of that.
Oh,
So basically,
okay, well,
it's
let's...
really, the proton is really based on hydrogen protons.
Uh-huh.
Always. Is that always? Or,
Yeah.
okay, so.
Let's work another one then, okay? Remember, read the words here. Think about the words. We're going to look at the side of the equation that we have, and we're going to fill these in one at a time. We're made fluoride, okay? In an acid-base reaction, we made fluoride. So, what you ask yourself is, what species gave up a proton to form F-? That would be HF. This is the conjugate base. This is the Bronsted acid. What species gains a proton to form hydronium? Water plus a proton gives hydronium. Therefore, this is water, and there we are. Let's do another one. We have chlorate. This is hydronium. What are we going to get? In this side of our reaction, which one of these guys is going to be the Bronsted acid? Bronsted acid is the proton donor, isn't it? Which of these two is going to donate a proton? Hydronium is. Frankly, it's the only thing with a proton.
So hydronium by itself is considered an acid?
Yeah.
Just by itself? Isolated.
It's a Bronsted acid. Proton donor. All right, so let's start here with chlorate. What species is formed when our Bronsted base here gains a proton? It's going to come in as H plus, isn't it? Comes in as H plus. If we have H plus and ClO3 minus, it's neutral, and it's chlorous acid. Our second part here, this is our Bronsted acid, isn't it? Bronsted acid is going to lose a proton to form its conjugate base. If hydronium loses a proton, what does it form? Water. Simple acid-base equilibrium. Chlorate, hydronium, chlorous acid, and water. This is hydrogen sulfite. Hydrogen sulfide is going to react with hydronium to form something. Now, we know that hydrogen sulfide could be a Bronsted acid, couldn't it? It could lose that hydrogen. We also know that hydronium is a very, very strong Bronsted acid. In this case, the strongest guy wins. If it ever comes down to it, hydronium is always the strongest. So, our Bronsted acid is going to be hydronium, and our Bronsted base is hydrogen sulfide. So the question you ask yourself is, what's formed when hydrogen sulfide gains a proton? All you're doing is adding H plus, aren't you? So it's going to be hydrogen sulfate plus H plus, and that's sulfurous acid. When water loses a proton, when water acts as a Bronsted acid, it loses the proton. What does it form? Water. Any question?
In this example, the reaction happens at any temperature or a specific temperature?
No, this is, all these reactions go typically at room temperature, is where you would do it. There's, when you have an equilibrium, you don't know this, and you won't know it till 140, but when you have an equilibrium, it is sensitive to temperature. So as you change the temperature of the system, you shift the position of the equilibrium. So that's why it's important to say this is at 25 degrees. All right. We said that we had strong acids. They gave up one proton each, right? And we call those monoprotic acids. We said we had sulfuric acid, which could give up 2 protons. Forms 2 moles of hydronium, and that's a diprotic acid. We refer to these simply as strong acids, correct? So we all know this now. We also have strong bases. Now, we addressed this in the problem from chapter 7. We said that sodium hydroxide ionized to give this pair of ions, but in fact that's an equilibrium. It can ionize and it can go back. But the process of going back is very, 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 very slow. This is very, 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 very fast. Therefore, in solution, sodium hydroxide exists totally, 99.999% as sodium and hydroxide. And remember, we said when we have neutralization, we're talking about hydroxide from a strong base, hydronium from a strong acid, giving water. Strong acid, strong base, and neutral water. Now, this is a really cute little slide. Please just appreciate it. This is my attempt to demonstrate this in very graphic terms. Here we have hydronium, this guy, and it's sitting here in a cluster of water. And we have chloride in here too. So this is meant to show HCl and water, hydronium and chloride. Strong acid, so essentially 100% ionized. Over here in this corner we have sodium hydroxide. Sodium cation, hydroxide anion. Strong base, 100% ionized. When we take and mix these two, hydroxide is going to react with the hydronium, pull off its proton, and sodium is going to go along for the ride. Pulls off the proton. We now have two waters where we had hydronium and hydroxide, and the only thing left in solution, sodium chloride. We have salt and water. This was so much work to make and so much fun to watch. We're going to watch it again. Hydroxide is going to pull off this proton, make a water, leave a water. Sodium goes along for the ride. Here's our proton transfer. 2 moles of water, sodium chloride. When a strong acid reacts with a strong base, you form a salt and water. Remember that phrase. Strong acid reacts with a strong base. You get a salt and water. Any questions? All right, well, we just formed water, didn't we? But way back earlier in the chapter, we said that anytime you have pure water, you actually always have hydronium and hydroxide. So when we talk about a neutral solution, it's not just salt and water. Remember, there's always a very small amount of hydronium and hydroxide that are present. Now we're going to return to the concept of neutrality in just a bit. But right now, let's just do another simple titration problem. This is like we did back at the end of chapter 7. Here we have sodium hydroxide. Its concentration is 0.025 molar. It takes 125 mils of it to react with an HCl solution that's also 125 mils in volume. What is the concentration of our hydrochloric acid solution? Okay, remember how we did this. This is an important calculation. Our stoichiometry here is 1-to-1, isn't it? So that's simple. we are given a concentration and a volume for sodium hydroxide. That means we know how many moles of sodium hydroxide, right? If we know how many moles of sodium hydroxide, that's the same number of moles of HCl. And if we know moles of HCl and its volume, we know its concentration. So step one, moles of sodium hydroxide. Concentration times volume is moles. 3.13 times 10 to the minus 3 moles. Now, we're looking for the concentration of our HCl solution. We know how many moles of sodium hydroxide we had, but because our stoichiometry is 1 to 1, this is the same as moles of HCl, isn't it? So moles of HCl divided by the volume, 125.025 moles. Now this was actually a test question, really was. And virtually everybody in the class did all these calculations. But did they have to? No. No. Think about it. We have the same volume of both, don't we? 125, 125. We have the same volume of both. If they neutralize each other, they must have the same concentration. So I set that up hoping that, at least the top few people in the class would just look at it right away and say, oh, 0.025, of course. Wow. Any questions? All right, well, let's look at some other test questions on this material. I'm looking for a pair of substances in which an acid is followed by its conjugate base. Okay? Looking for an acid followed by its conjugate base. A Bronsted acid does what to form its conjugate base? Loses a proton. Bronsted acid loses a proton to form its conjugate base. So what you're doing is you're looking for a pair here that differ by 1 proton. And the acid side has to have 1 more than this side. Well, the top one is stupid, isn't it? Here we've gained a proton. Here we have gained a proton. Here we have gained a proton. The only one where we have lost a proton to form something is this guy. Bronsted acid loses a proton to form its conjugate base. We have 0.5 molar sulfuric acid. We are reacting it with 20 mils of 0.4 molar lithium hydroxide. Now, lithium hydroxide is a strong base. Sulfuric acid is a strong acid. And we have 2 to 1 stoichiometry. So step 1, we have concentration and volume here. 0.4 molar, 0.02 liters. We have 0.08 moles of hydroxide. Now it takes 2 moles of hydroxide for every mole of sulfuric acid, doesn't it? So we're going to divide that by 2. 0.004 moles of sulfuric acid. Now, if we know the number of moles and we know a concentration, we can calculate volume. I'd rather do that. Doesn't matter which one you remember. Concentration, volume is moles. That works. You could do volume over moles is concentration. Whichever one you want to remember. Here I did this. Concentration, volume is moles. Therefore, volume is simply moles divided by concentration. We know moles. We know a concentration. Our volume is 0.008 liters or 8 milliliters. What's true about this reaction? Here we have hydrogen carbonate acting as a Bronsted acid, right? Water is acting as a Bronsted base. The conjugate base of hydrogen carbonate is what? Bronsted acid loses a proton, right, to form carbonate. All right, so which of these? Hydrogen carbonate's an acid? Yes, that's true. Water is its conjugate base? No. Hydrogen carbonate loses a proton. It doesn't form water. Hydrogen carbonate's an acid. Carbonate is its conjugate base. Absolutely, this one is correct. But let's look at these and see why they're wrong. Hydronium is an acid. Yes, it is. But this is not its conjugate base. Water is not acting as an acid. Hydronium is an acid. Carbonate is not its conjugate base. Remember, the Bronsted acid loses a proton to give its conjugate base. What is the conjugate acid of hydrogen sulfate? So this is the base form, isn't it?
Yeah, so CH2.
Conjugate base plus a proton is sulfuric acid. "50 mils of vinegar reacts with 0.774 molar sodium hydroxide. It takes 41.6 mils. What's the concentration of acetic acid?" We have different words here, but it's the same problem, isn't it? Same problem. We have a concentration and a volume for sodium hydroxide. Stoichiometry is 1:1. So we're going to figure out the moles of sodium hydroxide. 0.03. That's the same as 0.03 moles of this stuff. If we know we have 0.03 moles of this stuff, and it's 50 mils is its volume, this is 0.644 molar. Number of moles divided by the number of liters gives us concentration. All right, let's go back to this. I said we were going to use this a lot. We said that a neutral solution was going to have 10 to the minus 7 moles per liter of hydronium and 10 to the minus 7 moles per liter of hydroxide. That's what we have in a neutral solution. We're going to describe this using the notion of pH. Now, the exciting thing is, pH is a log function. So you paid all that money for your calculator, now you get to use the log button. pH is going to be the negative logarithm of the hydrogen ion concentration. Now, let's just remember back to 5th grade what a logarithm is. A logarithm simply refers to an exponent. We're at base 10. Whenever you use the phrase log, that refers to a base 10. Okay, so let's say we have 10 times 10. We can describe that as 10 squared, can't we? That's 100. So if I asked you what the log of 100 was, it's simply this exponent. So the log of 100 is 2. If we had 1,000, that's 10 times 10 times 10, 10 cubed. Log of 1,000 is 3, simply the exponent. If I told you I had 0.000001, you could write that as 10 to the minus 7, couldn't you? The log of 10 to the minus 7 is simply the exponent minus 7. Now when we take the pH, we're going to take the logarithm of something. And because it's a negative logarithm, we're just going to change its sign. So, let's see how this works. pH is the negative logarithm of the hydronium ion concentration. Remember, anything in square brackets like this means molar concentration. Sometimes you'll see this written as log H+, sometimes hydronium. It all means the same thing. When you see this little p in front, p actually is a shortcut for negative log. So if I say pH, I mean negative log of H. That's where the term comes from. All right, let's say we're dealing with neutral water, 25 degrees. We said in neutral water, we always have hydronium and hydroxide, don't we? And they're always 10 to the minus 7 molar. What's the log of 10 to the minus 7? Well, it's minus 7, isn't it? The negative log of that is simply 7. Therefore, and this is the great crescendo here, therefore, the pH of pure water is 7. That's where that comes from. Neutral, pure water has 10 to the minus 7 molar hydronium, log of 10 to the minus 7 is minus 7. Multiply it by minus 1, we get 7. That is the pH of neutral water. Now the important things to remember. If we have more than 10 to the minus 7 molar, let's say we had 10 to the minus 3 molar, so that's a lot, right? 0.001, as opposed to all those other zeros. So we have a lot more. We take its log, change the sign for 10 to the minus 3 molar, this would be 3. We have more hydronium than we do at neutrality, therefore this is an acid solution. If the pH is less than 7, it's acidic. If the pH is greater than 7, means we have less hydronium, so it's basic. 7 is neutral, less than 7 is acid, above 7 is base. All right, let that sink in for a second. Just like we have a pH scale, we can also have a pOH scale. Remember I said P stood for negative log, right? Negative log of OH is simply POH. All right, now watch this magic. In neutral solution, hydronium and hydroxide are both 10 to the minus 7 molar, aren't they? So the pH is going to be 7. The pOH is also going to be 7. If we were to take and multiply hydronium times hydroxide, we would get 10 to the minus 14. Right? 10 to the minus 7 times 10 to the minus 7, 10 to the minus 14. We just said for neutral water, this is 7. pOH is also 7. That's 14. Under all conditions, hydronium times hydroxide is always going to be 10 to the minus 14. And under all conditions, pOH plus pH is going to be 14. You get a 3x5 card on this exam, that's something you might want to write down. pH plus pOH is going to be equal to 14. If our pH is 10, that means our pOH must be 4. If the pH is 1, pOH must be 13. All right. If we know that this relationship is always true, hydronium times hydroxide will always be 10 to the minus 14. If I give you hydronium or hydroxide, you can calculate the other one, can't you? So, if I tell you that our hydroxide is 5.04 times 10 to the minus 8 molar, what is hydronium? All you have to do is take 10 to the minus 14 divided by our hydroxide, and that will give us hydronium. All right, well, this is a lot of fun, but it's a little scary because there's a log and all that stuff involved. So let's just calm down a little bit and let's just talk about the pH scale. We know the neutral things, water, plain neutral water, is going to be 7, right, by definition. Slightly on the basic side, blood, sweat, and tears. Going up top here, very, very basic. Sodium hydroxide, 1 molar, would have a pH of 14. Going on the acid side, here we have bad coffee at about 5. Tomatoes, about 4. Cheap wine is about 3. Stomach acid is 1. Isn't it amazing you don't dissolve yourself? Stomach acid is 0.1 molar hydrochloric acid. Astounding. And if we had 1 molar HCl, our pH would be 0. pH can actually be negative, and it can also be above 14. However, whether it's positive, negative, whatever, pH plus POH is always 14. How do you measure it? Well, this is what's called a pH meter. In 140, you'll probably use something like this, nothing nearly this fancy or sophisticated. What this actually is a millivolt meter. You have a little, very thin glass membrane here. By very thin, I mean the thickness of a hair. And you bump it against the side of the beaker here, it breaks, and they charge you $100. So you don't want to mess with them too much. But you set up a potential across this little membrane here. The voltmeter reads it. You calibrate it with standards, and therefore you can determine a pH. Much simpler and unbreakable is pH paper. And you can take a piece of this remarkable paper and simply dip it into your solution, and it will change from this pale green to these different colors depending upon the pH of your sample. Kind of really neat stuff. pH paper works because there are a thing called indicators. Now, we saw an indicator in lab, phenolphthalein. This is what phenolphthalein looks like. This is its ball and stick model. This is what it would look like in organic chemistry as a real model. Phenolphthalein in acid solution is colorless. When you hit about pH 8, it turns this pinkish. You notice that some of these guys have lots of transitions involved. When you make pH paper, what you have is a mixture of these different dyes, very carefully selected and calibrated so that you get a given color depending upon your pH. Any questions? Well, the experiment that we kind of did in lab in a stupid sort of way involved taking base we were doing and adding it to an acid solution. In real lab, you do this using what's known as a burette. Burette looks like this, and it's calibrated in milliliters. You have a little stopcock here so you can release this stuff drop at a time. And down in here, you have your unknown solution and an indicator. And what you do is you dribble this in very slowly, waiting for the color change to happen. It looks something like this. You read up where you start, so we're exactly at the 10 mil mark. Open our stopcock. get your color change, stop it, and then you can read where you wound up at. If you take your final reading and your initial reading, you know a volume, don't you? Concentration and a volume, you know how many moles you added. If you know how many moles you added, you know how many moles were in your unknown. So this is what we do when we do a titration. Let's just look at one more of these. We have 20 mils sodium hydroxide titrated using HCl. That's 1 molar. We start at 10, we wind up at 25.6. What's the molar concentration of the sodium hydroxide? Well, what do we know? We know stoichiometry is 1 to 1. We know a concentration and a volume. So initial and final gives us our volume. Concentration and a volume gives us moles. Once we know moles and we know a volume, we get our concentration. Same problem over and over and over again, isn't it? Moles of HCl, 1 mole per liter. That's our volume, 15.6 mils. We have 0.0156 moles. That's how many moles of sodium hydroxide there were, right? Therefore, we have 0.0156 moles of sodium hydroxide, 20 mils is 0.02 liters. This is 0.78 molar. So that's what you use these indicators for in lab. You do titrations like this. We're not actually going to do one in 110, but in 140 you would do a lot. Any questions? All right. Let's look at this one. I tell you that I have a solution and its pH is 7.23. What is my hydronium ion concentration? Now you need your calculator. We remember pH is simply the negative log of hydronium, right? But what we want is the hydronium. Our pH is given as 7.23. You know, this negative sign just kind of makes me nuts. So let's move it to the other side. Just get rid of it. Move it to the other side. So I could say minus pH is simply log of hydronium. Okay? Now, remember, we said that the logarithm is simply the exponent for the base 10. So if I took and I said I had 10 to the minus pH, then the logarithm of that would be pH, wouldn't it? Minus pH. If I said I had hydronium, and its logarithm would be log hydronium. This is the process of what's called taking the anti-log. That's the thing that is its logarithm. So, very functionally here, here's our pH that we were given, 7.23. We made it a minus pH. That is our hydronium ion concentration. Again, very operationally, what do you do here? You take your pH, you change its sign, you do 10 to the minus pH. This is what my calculator looks like. Yours is different. On my calculator, I have a button labeled log, and above that, I have 10 to the x. Many calculators have a 10 to the x separate key. Some of them you have to, this one you have to push the green button first. So how would I get my hydronium ion? I would type in minus 7.23. Now on my calculator, I'd push the green button, and then I would push this guy. And I get 5.884. 3644 times 10 to the minus 8. Now clearly that's way too many numbers, isn't it? So here I've just rounded it to 3 digits. So I could say my hydronium ion concentration is 5.89 times 10 to the minus 8 mole. Now I'm going to teach you something that nobody else in this building probably knows. Okay? This is the wrong answer. Why? Because a logarithm like this, 7.33, is actually a power of 10, right? If we had a number in scientific notation and we asked how many significant figures you had, the 10 to the whatever, you wouldn't worry with, would you? Just the coefficient. The first digit in a log is simply the power of 10 you're dealing with, called the characteristic. But you don't count that for significant figures. In a pH value, all of your significant figures occur after the decimal. So this only has 2 significant figures. That means that this properly is 5.9. Now, like I said, nobody else in this building probably knows that. Back at UIC, class would go in to meet with their teaching assistant. The TA wouldn't know it either. And they would argue. But you know it, and I know it. Of course, I am not going to be a sticker on this, but that's the way it's done right. You look at the number of digits after your decimal, that gives you the significant figures. All right, let's do this in real time. Take your magic calculators, take these pH values, and give me hydronium ion concentrations. For our first one, we would type in -4, right? Then we would hit 10 to the x. And we would get 10 to the minus pH is 10 to the -4. Our hydronium ion concentration is 1 times 10 to the -4 molar. For our next one, our pH is 12. We're going to go 10 to the minus pH. That is 10 to the minus 12. So you see, if the pH is a nice even number, you can do this in your head, can't you? If we are at 5.5, on your calculator you type in minus 5.5, hit 10 to the x. 3.2 times 10 to the minus 6. Type in minus 1.32. Hit 10 to the x. 4.8 times 10 to the minus 2. And finally, we have 7.025567. Is this solution acidic or basic? It's basic, it's above 7. Type in minus 7.025567, hit 10 to the x. We have 9.42829 times 10 to the minus 8 mole. Now, isn't that fun? It is. So much fun, let's do it the other way around. If I tell you we have 7.042 times 10 to the minus 7 molar, what's my pH? Well, why do we remember? This is our hydronium ion concentration, that's given. We know the pH is simply going to be the negative logarithm of this thing, right? So what we're going to do is take the log here and multiply it by minus 1. Here is my calculator again. I type in 7.042 times 10 to the minus 7. I look around, I find my little button labeled log. I simply push it. And I get minus 6.15. To get my pH, I have to multiply it by minus 1, don't I? My pH is 6.153. Once again, for significant figures. How many significant figures here? There are 4, aren't there? So we have to have 4 digits after our decimal. I'm not gonna test you on that, but that's the way it's done. All right, let's do this one, and then we're done. If I tell you my hydronium is 1 times 10 to the minus 4, what's my pH? You can do that in your head, can't you? 4. 5 times 10 to the minus 4. This one you have to type in. Type in 5 times 10 to the minus 4, hit the log button, change the sign. 3.301. $1.371 times 10 to the minus 8. Type it in. Hit the log button. Change the sign. 7.86. I actually, in a slightly different context, put this on an exam. 7 times 10 to the minus 7. You have no idea how many people simply said this was pH 7. But of course it's not. That would be 1 times 10 to the minus 7. Therefore, simply type in this number, hit the log button, change the sign, 6.15. And our last one, 4.61 times 10 to the minus 5. Type that in, hit your log button, change the sign, 4.336. Now, we're going to do this next time. We're going to start off with this on Friday. But if you want practice, there are 2 very simple tutorials to do with pH. You have this one. Come on. And we have this one, where you're given one, and you have to type in all the others. Very good practice. We'll start off with this on Friday. Wednesday, we do lab number 7. And we're going to do the magnesium part, not the copper part.
Before you said that don't count this one for the scientific, so it should be 3 not 4, right?
No, this is most significant figures. That's a number. So we need 4 digits after our decimal.
Okay, so look at this and then count them more without counting this one, but then 4 places here. Okay.